Okay. All right. Thanks everyone for being here, and thanks Indrė for accepting the invitation and being with us. And Indrė is an associate professor at the Department of Computer Science here at the University of Helsinki, and she is going to talk about interesting topic, which is cross-validation, but not just cross-validation, but cross-validation revisited. So we're going to see something new about this kind of old topic. So let's see what we have to learn today. Thanks.
Thank you. Yeah, my pleasure. So it's my third time at the FKI seminar, so I wanted to come up with a topic that's that I don't repeat myself, at least not too much. Yeah, so revisited, indeed, it indicates that it's an old topic, but today we're going to talk mostly about circumstances where data is not well behaved. So we'll see what's new or what's potentially brewing in there. Quite some of the work that I'm going to show is work in progress, so I don't know all or many answers myself yet, but we'll see. So, it's a rhetorical question: how do we know that the machine learning model works? And the title of the talk kind of suggests already the hints, but anyone could help to start this revisited topic. What are the ways that we might know or not that something that we made, that we trained, works? Yes, no? Right. Anything else?
Information criteria.
Mm-hmm. Yeah, so basically that summarizes. So either we know from the model statistics that we already get from the training data that it's reliable, and if we believe that the modeling assumptions are satisfied and we believe the statistics, we might not even do a separate testing, but usually and hopefully we often do. And if we think about testing, so especially testing in practical circumstances, so we can think of online testing and offline testing. Online testing, known as A/B testing or randomized trials in medicine, where model that's made is actually put in operation and tested in real life or real time or semi-real time. Online testing is often preferred, but usually is not quite feasible. So we are left one way or the other with something that generally can be called cross-validation, that is pretending, especially in the supervised learning settings, pretending that we don't know the outcomes for part of our data set and then try to simulate as if that was unknown data and see how our models perform on that. So that's very classic. And before going into more technical details of what I'm going to talk about today, that is non-classical circumstances of cross-validation, I just wanted to spend some minutes of thinking of what machine learning models are for usually, and what they are for, not in in task formulation, but in terms of knowledge that is either being generated or used as part of machine learning. So the largest, probably the majority of models in practice, and quite large part in academic context as well, are machine learning for automation tasks, we may think. So that's something that humans can do, but models would do either more effectively or more faster or more efficiently or alike. So examples include many classical examples, including machine translation. More exotic example from my own work could be chemical monitoring of chemical production process, where there are lots of sensors, and so there are huge factories that produce, for instance, acrylic acid or anything that's required in for our production of our consumer goods. And so the idea is to use machine learning models to monitor what's the quality of the output that's coming out based on sensory data. And so the quality can be verified with somebody coming with a bucket, not a bucket, but like taking a sample of the production process, bringing it to the lab and finding out. But so the idea is of automation is to have it faster, more efficiently, and more often. So for automation, so usually people can verify, and it's sort of replacement of human expertise. So labels are, ground truth labels are available, and usually at a cost, but it's not impossible to get. And so if needed, we can even generate separate testing sets or do something that resembles online testing as well, if we want to, and if we want to pay the price for obtaining the labels. And then if we think further of what machine learning can be for, so we can think of machine learning for forecasting in a broad sense. Again, here I mean in a broad sense. Examples can include anything that we do with user modeling for advertising or any related tasks. So predicting user actions after having shown some content. Credit scoring could be for forecasting. So predicting credit risk of, or whether the person, the receiver, will repay the loan or not that's being granted. So this is about something that humans could know or could also forecast if they wanted to, but it's not directly replacing human expertise for what human can already do, but it's more about well, predicting the future, if you will. Another example would be predicting travel time, say from Kumpula to Helsinki downtown in an hour from now. So like human could predict, but the ground truth is not directly ground truth, even if human makes that ground truth. So the difference here is that the outcome is usually not, the ground truth is known quite easily, but it takes time. So when time comes, we sort of usually get either automatically or semi-automatically, we know the outcome. And so if we are ready to wait enough time, then we could also potentially gather separate additional training sets or even do semi-online testing outside our training data completely. So if we wanted sort of an independent test for our model. And the third category, what for? So I would like to distinguish is for knowledge discovery. So this is usually used more in academic context, but not only and not completely. And this is perhaps where my group's work nowadays mostly is machine learning for knowledge discovery. So for discovering something that we don't know. So the purpose of making models is that we want to know, and so we usually want to know the internals of why the prediction is this way. And in those circumstances, so naturally labels are unknown, or they in principle cannot be known directly, because if we knew, then the task wouldn't make sense, if it would be easy to collect that knowledge otherwise. So even our training data, or our in a broad, I'm saying in a broad as our machine learning community. So the training data is usually not quite directly related to what related, but not immediately related to what we are trying to discover, or we are trying to generalize in some ways. So medical research is one example. So does smoking cause cancer could be a sort of very classical old question, but questions of that kind. Comparison to forecast, in comparison to forecasting, so for forecasting would be a clinical question would be, here is a patient, can we predict what would be the best treatment given that concrete patient? And for knowledge discovery would be more like, in general, for all kinds of patients, would this treatment be more effective than that? For knowledge discovery can also include, another example that I have here, can also include, say, anything that we may want to argue about, circumstances that are not there yet, and in long distant future, for instance, climate change could be one. So if we wanted to to analyze what would be community structure of fauna and flora 20 years from now, given concrete circumstances. So there is no direct way of knowing the outcome. So we can test such questions on data that's collected today or in the past, but for the very concrete and very actual question, there is no way of knowing. And so, so we cannot do online testing, and even we can argue that our validations or cross-validations in such circumstances would be indirect. So what should we do? Okay. So yeah, and the time is, oh, okay. So I'll talk faster. Right. So so that brings, so we cannot do online testing as often as we would like to. And even if we do something that resembles sort of, we simulate a testing set that may or may not be directly related to the task that we are trying to address when making machine learning models. For automation, it's fine, but for knowledge discovery, it's more challenging. But so if we are in these circumstances and still we want to do something, there is not much more that we can do. We still want to do cross-validation of some sort. So what are the nuances? What are potential nuances and challenges there? And so the classical cross-validation that's illustrated here, and everybody knows, partitions all the available training data into parts and pretends that for one of the parts pretend that the outcomes are unknown, and then tries to predict and then checks what's happening. So this is very classical textbook stuff. An important part of this is that there is a fundamental assumption behind classical cross-validation that the data is independently and identically distributed. So independently means that each sample is drawn from the underlying distribution independent from each other. And identically means that throughout the data distribution is the same. So for instance, there is no concept drift, or transfer learning also violates that assumption, for example. And so, so in the rest of this good half an hour, I'm going to talk about circumstances where these IID assumptions are or might be violated, and what the implications might be for doing cross-validation, and what kind of cross-validation can be done in those circumstances. So one of the first cases that I want to concentrate is that data is non-independent spatially. So if we think of data that comes from anywhere on Earth with any sort of geographic background to it, so the first law of geography, which is quoted here, says that everything is related to everything else, but near things are more related than distant things. And this is very intuitive, and we all know that. And the images here illustrate an example of university campuses. So this is Kumpula, this is Viki, this is Turkana Basin Institute in Kenya, where we sometimes work, almost in a desert. And this is a university center in Svalbard, up north. So this is just a toy example to illustrate that if one wants to do something like remote sensing, for instance, predicting anything, properties of the surface of Earth. So things that are nearby, even visually, look very similar. And if we try to characterize them describe them by quantitative features, they would probably look in our data space like near duplicates of data. So like almost identical copies of data. And so what happens if near duplicates copies of the data, and if we do cross-validation, they end up one in the training set, the other in the testing set, we have data leakage, what is often, we have what's often referred to in machine learning as data leakage. So that's as if we are really measuring not anything like a testing error, but more like a training error. So we have near copies of our data set. And so this illustration shows how it can happen if we do a simple cross-validation with geographically obtained data. So these are coordinates, but we may even not have coordinates in our original data or original feature space. If we just take, say, data from somewhere, so points that are nearby, like in the example with Helsinki and Kumpula, will be similar to each other. And this is how yellow points here show how cross-validation would distribute points over 5 folds. So like each fold would have points that are very nearby each other, some of them in yellow, some of them in blue. So that means ending in training and testing sets. So this way we may have what is called data leakage, and this may or may not be bad depending on the circumstances, but at least it's often hard to call it testing or validation error. It's often would be something that what we are measuring would be more like a training error. So that leads to that might lead to circumstances where error estimates might be too optimistic, and too complex models might be favored in model selection. So again, as if we are selecting more like from the training data. So to overcome that, people have this has been around for a long time in GIS systems, and people have overcome. People come up with something that's called spatial cross-validation. So essentially stratifying folds. And now we see that so most of the blue points would be far away from yellow points spatially, and presumably then that would solve the problem of not leaking the training data into the testing. To fully to be on the safe side, it's also a good idea to have a buffer zone. So this example illustrates. So red one here would be our testing fold in the cross-validation. So the gray ones would be completely thrown out, both from training and testing in that fold. And then the blue ones would be the training points, such that none of the blue points are near the red points. And so how far and how large buffers should be, it's again a matter of empirical reasoning and testing, and it can be different, but the principle is that sort of to isolate training and testing folds. And leave one out also can be done in a similar way. So if we have one point that we select for validation in leave one out cross-validation, then we choose a radius around and we throw away points that are within the radius, such that our nearest training point is not too near of our to our testing point. So that's known, and so it may or may not be important. Is sort of it may be more or less relevant depending on the circumstances. It's of course, as with any risk of overfitting, so it's more relevant in cases of models that are complex as compared to the data size. And so this example illustrates a recent work of my student, just testing with feed-forward neural networks of many layers in the order of 100 on the global data set to see how training and validation error behaves. So this is random cross-validation, training and validation error completely overlaps, and this is with increasing size of the buffer of isolation. And so with large enough buffer, then we start seeing that the training error is become with enough epochs. So here with enough of potential to overfit, we see that the training error is becoming significantly lower than the validation error, and that's what would be expected under overfitting. So this testing is done actually. So this example, this testing is done something that would be like a double cross-validation. So the areas that are in blue with black dots would be the standard cross-validation, and then one continent at a time would be yet another validation fold for after doing the cross-validation, then having the test. And so this is what might be sort of the most prudent, but there is a nuance here that I have to now speed a little bit up, and I'll jump to what I wanted to say right away. So the nuance is that if we do blocking, if we do spatial isolation to try to get rid of structural dependence, so in order to not to leak training data into the testing set, what we are risking of doing is we are risking to actually create non-identically distributed data. So if our spatially speaking, if our data, if each of the continent is represents data from slightly different space of the data distribution, and if we if we overdo the isolation, so along with isolating one point or a set of points for testing, we may also exclude part of overall distribution. So an example of that might be here. So here we have yet another task from our group predicting species distribution of Asian elephants. This is what's called tetraminoblock cross-validation. So I'll leave out for another day explaining how it works, but the main principle is that, for instance, if we take one fold that is there as a testing fold that represents the highest mountains on Earth, so that means that our testing set will represent conditions that are nowhere else in the data set. So if we were to do random cross-validation, then some of the, like in the random cross-validation, our testing fold would contain representation throughout the whole space of data distribution. Whereas if we do blocked cross-validation to avoid potential data leakage, what we may create is that we with the blue one there, we would completely isolate one kind of environments that are available. And this may or may not be desired. So what I want, if there is one thing to remember from today's talk, is this one, that it's a trade-off. So data leakage versus extrapolation. So if we do blocked kind of cross-validation, then we prevent the leakage, but then we increase the risk that we are extrapolating to tasks that are unseen in the model training. So, and if this is what we want to test with our testing procedure, that's an ideal situation. But it may or may not be so. And so this is still work in progress. So where exactly the trade-off is probably often an empirical question, but that's how it is. And this is just to quickly show a case study from this tetraminoblock cross-validation. This is a case study of predicting species distribution of suitability of conditions for Asian elephants 40 years from now. So this is somewhat hypothetical task, but it's relevant for conservation and understanding, knowledge discovery and understanding of ecology and macroecology in general. But from the machine learning point of view, the important part is that here that these blue and red are predictions based on a model where feature selection was done using random cross-validation, like the usual randomized cross-validation. This is a model, so blue are positive predictions and red are negative predictions, so not suitable or suitable. And these are done with a model that was trained using feature selection for many features, usually climatic features, with spatial cross-validation, like I just explained. So visually, we see that they are different, quite different here. The original training data was only from this region, so there is also extrapolation naturally in this task. The main point here is that the predictions are very different, and we have no way of knowing which one is the right one. But from the discussions with experts and with elephant researchers, this seemed to be more reliable. But this comes back to what I tried to describe in the opening of types of machine learning tasks. And this is a task of knowledge discovery, where we are doing the modeling for the purpose of knowing what we don't know. And so there is no way, whether we do spatial cross-validation or any other cross-validation or any kind of testing, there is no way of knowing from the data which of the options is right. And the options come differently because models do test it in these different ways to different feature selections. And so this model is sort of potentially overfitting more to the region where the original distribution data comes from. And that's where these elephants are, Asian elephants are today, and these are around South Asia today. So that's the point. It's a trade-off, and it's not clear which one is right without external knowledge or trying to verify. But it's a good idea to consider spatial or any other structural dependence in data, or be aware of potential data leakage in this way. So this structural dependence is not only spatial, that can be very different ways. And I'm not gonna go into more details today, but just to mention that very similar problems or challenges can occur in data that's related phylogenetically. So data that things derive from common ancestry. So this can be anything of the living world, nature, animals, plants. This can be patients in medical research, like patients that have of the same family would be more related to each other than patients from somewhere else. If thinking very hardly, one can also think of spatial dependence as hierarchical dependence in a similar way. So places nearby versus places far away. And so same principle here with structural dependence is that if we have data points that share common ancestry more recently, then they are closer to being more as if they are copies of each other or near copies of each other. So when testing or even when making models, that's a topic for another day, but especially when testing, we often may want to think of how to balance out such that if our data distribution is such that we see that we can potentially have 3 kinds of animals or four kinds of animals or plants. If we were testing on each observation with an equal weight, so this set of near copies would outweigh the we would have as if they are near copies of each other, and same problems like in spatial in the spatial circumstances. So there are solutions for phylogenetic cross-validation in a similar way. So one of the simplest one is to block branch or branches and such that they are completely isolated when they're used as a testing set. This diagram here illustrates frequency of model selection. So the darker in blue, the more frequent is the model selected as the most accurate. And the vertical axis is the number of parameters. So up are 2 parameters and downwards are 10 parameters. So the lower, the more complex is the model. And we see that random cross-validation is more blue here, whereas blocked and different variants of stratified cross-validation is more blue upstairs. And this means that with more likely to overfit with random cross-validation. So random cross-validation selects more complex models on average than stratified cross-validation. And this is again the same trade-off between blocking and extrapolation, same argument as in the spatial case. So, and then, so back to non-independent and non-identical distributed data. So with these examples of spatial, phylogenetic, cross-validation, so I touched upon non-independent sampling of data points. So data points that are related to each other and make near identical copies of each other. That may be harmful if one ends in the training fold, the other in the testing fold. Time series is also very similar. So points that are nearby in time are often more similar to each other. And lots of time series research actually draws on that. So autoregressive moving average models are actually models that take this structure into account and extrapolate from what has been observed the most recently to the next point. So similar. So circumstances are similar with time series data, but with time series data or data that is observed or recorded over time, again, even if it doesn't have time feature in the feature space, but it's just sort of a sequential observation. There's another challenge of non-IID, so the second I, so that the data is non-identically distributed. So meaning that part of the distribution is part of the data is from one distribution, and then something changes, and then distribution becomes different. So this example illustrates a time series of predicting, again, from chemical production process, predicting the quality of output, where the red one is the ground truth that becomes available over time, and the black is a soft sensor, so it's a predictive model, statistical, not quite machine learning in our modern sense, but predictive model that predicts the outcome. And we see here that something changes, that the model goes out of tune. So the little ups and downs are still in sync of what is happening. So for example, here the ground truth goes down, and so the prediction also goes down, but they become out of tune. And so that's one very standard example of concept drift, where the distribution of the target, conditional distribution of the target changes as compared to the input data. So concept drift requires adaptive machine learning modeling, and that's also by now quite an established field or branch of machine learning. And testing such models has its own specifics. So cross-validation like standard cross-validation doesn't really make sense if we test adaptive learning models, because adaptive learning models need to update themselves automatically over time. And so the aspect that is being tested is usually the capability and accuracy of those updates. So cross-validation, simple cross-validation just doesn't work. So what people usually do is what's called frequential evaluation. So simulate arrival of data over time. and use all their data as training, then test on the most recent data points, and then pretend that the labels are received, check the performance, and then train models again, including those new samples, and then receive the next point, and so on until the whole available training data is exhausted. So this is also like cross-validation in the sense that it uses all the available training data for testing in terms, but the terms are not random, but they are specifically ordered in time. So this is quite standard, and it works pretty well in practice, or like at least in research practice for properties of adaptation. But there is another nuance here to take into account when thinking about cross-validation, is that overfitting may happen in different ways. And here overfitting may also happen in terms of overfitting to change points. And I could happily give the whole lecture on this topic, but to be very brief, we can think about a situation like this. So this is also from our work in chemical production plan. So this is the original data, and we see that some change happens here that we would potentially want to adapt to this. So suppose that this is our prediction target. So the input features are not shown here. So suppose that we want to adapt to this. Suppose that we have two kinds of concepts. So say suppliers of raw material brought supplies that are of lower quality, and everything gets in this level. And so the vehicles probably are still depending on what the operators do, but sort of suppose that we have sort of two states of what can be there. And so for this original data, so we have much longer observation time before the change happens, and then change happens. Here we have much shorter observation time, almost identical circumstances, but so the situation is reversed. And so if we have data sets that are where changes happen, but changes do not happen so often. So we have, say, this can be months or even years of data, and we still want models to be adaptive to such changes, and we may want to test or with variants of cross-validation how to adapt to those changes. So the second type of overfitting that can happen is overfitting to actually configuration of changes. And this can happen because adaptation depends on what has been learned previously and for how long, how fast and how reactive is the reaction to change, and how long is the stable period after. And so I'm sorry, I have to skip some of the content, but the main message is here is that effectively, when we are testing adaptive learning models with frequential evaluation, which is a form of cross-validation, so we can overfit to changes to where in time the changes are and what's the magnitude of the changes. So an illustrative example here very quickly shows that different classifiers might perform differently on different portions of data and different configurations. And so this is, I'm skipping, but this is just to illustrate the point that that the testing of the adaptation depends on where and how changes are configured in time. And so if we have only one or two or a few changes per whole block of training data that we have, we may want to test it with multiple or multiple runs, or as if we were doing cross-validation of some sort with randomized folds in the classical cross-validation. So one way to do is to do permutations of the data over time. But if we do just simple plain permutation, we destroy all the changes and we just get random order. So our data distribution becomes uniform. So we lose different data distributions from different places, and adaptation becomes meaningless because there's nothing to adapt here, because there's just all the data is all the same. So we could have static model here for this example. So, so to finish, so what we can do is we can do something like cross-validation folds, not quite, but something randomized versions, where we do controlled permutations to preserve local distributions. And for that, we can get inspiration from shuffling of cards. So this is Persidiakonis, one of a famous mathematician, one of the authors of he's famous for the widely known notion that it takes 7 shuffles to fully mix a deck of cards. So, like, sort of, if we expect this, so it of course depends on the length of our sequence and many other sort of the protocol of mixing, but we can use similar principles to do cross-validation for temporal data when we are aiming to test the adaptation properties. To avoid this, and generate permuted versions of this such that we still control local distribution, so such that we don't fully destroy them and we preserve actually non-identical distribution of data. And for that, I brought cards to do a demo. So we finish with the demo. This is so these permutations and cross-validation ways have mathematical guarantees, and there are they are described more rigorously, but just today I'm just showing it visually. So this is a deck of cards that illustrates the history of Earth. So from today to 4.6 billion, so 4,600 million years, and it will serve for us as a time series today. So they are sorted from 0 to 4,600. So what we are aiming at when we do permutations of sequences or our sequential data for testing adaptive machinery. So we are aiming that if we take a little portion of data, like from here, so that still the local distribution is preserved. So we sort of in a sequence. And so the first permutation is called time permutation. So it's just a simple card shuffle like this. So and what it does, it actually creates. So the sequences are still mostly preserved, but it creates several breakpoints. So it sort of changes the order of how changes happen. And sometimes if there is trend in the data, this can also introduce abrupt changes. But if we don't have time, but if you were to come closer and see, so most of the sequences are preserved, but there are several breakpoints and they are in a different order. And so we can do this in a randomized way, every randomized way. So with a randomized split, split will be at a different place. And we can do multiple tests with such a time series for adaptive machine learning. Second is shape permutation. So it's another like this. So you get the idea. Sorry, the online people don't see. Well, next time you come. So it's like this. Well, you get the idea, and there are again mathematical guarantees of how much is preserved and how much is destroyed. So the actual sequences are no longer in complete order, but they are still resembling the original data. So we don't get this, and we can do again this in a randomized way and to test adaptive machine learning. And the third is a speed permutation. So it's also from card shuffling, and we lift at random and we move forward. So we make data run twice as fast. and so it will have double the amount of changes that the original data had, and there will be one break in the middle. Anyways, and again, we can do it in a randomized way, and so with our data and test adaptive machine learning strategies. So yeah, and so this is an illustration in one of the examples, so that the original frequential validation, so like cross-validation, this would only give one value of accuracy for one sequence for adaptive machine learning, whereas with controlled permutations, one can then do multiple versions and see the variance of the accuracy and different changes. So I think we are out of time, and I'll stop here. So I started about how we know that the machine learning model works. So hopefully we know somehow. Most often we know it from our training set, on which we do cross-validation. And I covered different circumstances, briefly covered different circumstances where standard cross-validation may not necessarily work in ideal ways. And I highlighted a trade-off that if we do a block cross-validation, either in spatial or in phylogenetic, or even in time series if we wanted to, I didn't cover that today, but if we do blocked cross-validation instead of random, then we can get rid of potentially prevent data leakage, so potentially prevent having near identical copies of our training data into the testing set, but at the same time we create so we create non-identical data distribution this way. So so with blocked cross-validation we can isolate a portion of data from our training that is somehow unique, like with the example of Everest Mountains. And we may or may not want that, so it depends on what the goal is. And usually if we are working for knowledge discovery type of machine learning tasks, then one way or the other we want to extrapolate. So usually our task is somehow to discover something that is not easily knowable or is not easily known. So we are in a setting of extrapolation in those circumstances, and then we probably want that. I mean, that's not a bad thing if we isolate and test on completely unseen distribution. So thank you, and sorry for going over time. Thank you.
Yeah, thanks. I think our timing was good, so that we had some technical issues. But we have any questions? Yeah, or yeah, no. So